methanol, or commonly called as methyl alcohol. So methyl chloride is going to react with this nucleophile to generate methanol and chloride ion. So the formation of this methyl chloride follows second order, follows a nucleophilic substitution reaction, that is a bimolecular reaction where it is SN2 reaction, follows SN2 reaction. This reaction is known as SN2 reaction. Methyl chloride reacting with the nucleophile to form methanol and a chloride ion. This reaction is known as SN2 reaction. So in this kinetics, this is a second order kinetics, which indicates the rate of reaction depends upon the concentration of alkyl halide as well as nucleophile. Concentration of both the reactants are very important in this reaction. That's why it is called as second order kinetics. And because of this second order kinetics, it is called bimolecular substitution reaction, and it is denoted by SN2 reaction. This is what about the kinetics here. Then coming to the mechanism, it is a single step mechanism in which the methyl chloride reacts with the nucleophile OH. This OH is also rich in electron. This chloride ion is also rich in electron. There is a repulsion between both of them. That's why this OH cannot act on front side of the molecule. It will always attack at the rear side of the molecule or a back side of the molecule. Clear? And the energy to have this, all this is where this chlorine is an electronegative atom. It always tries to pull the bond electron towards itself, thus creating delta minus, delta plus over the carbon, and the covalent bond is converted to polar bond, that is a weak bond which can be broken very easily. So because of this particular arrangement in a molecule, which is always there in this molecule, so there is attraction between this positive charge and a nucleophile. It is simple acid-base reaction happens. So the collision between the alkyl halide and a nucleophile generates certain amount of energy. That energy is more than enough to react this OH with the carbon, the nucleophile to a carbon, and in transition state it looks like this, where the OH is trying to form a bond with the carbon, and the CH3 I will write in this fashion. 3 hydrogens are attached here, and at the same time the chlorine is trying to break a bond. All this process is a simultaneous process. So in this transition state, what you are finding is the O is forming a bond with a new carbon, nucleus of a carbon, and at the same time the halogen is trying to break a bond between carbon and the chlorine. So thus ultimately what it forms is a methanol plus chlorine comes out from the carbon taking bond electrons as chloride ion, but ultimately what is formed is a methanol is formed. This is what the reaction mechanism involved in this particular SN2 reaction. It is a single step mechanism where the nucleophile attacks the carbon at the rear side, back side, because it cannot act on front side, because front side is the chlorine atom, which is also rich in electron, whereas your nucleophile is also rich in electron. There is a repulsion between both of them, so it cannot act on front side or where the chlorine is attached. So it will always attack at the opposite side of the chlorine, that is rear side or back side, what we call. And the collision between the nucleophile and the alkyl halide generates certain amount of energy. That energy is more than enough to form a bond with oxygen and carbon. And after the bond formation of this oxygen and carbon, it also generates certain energy. that energy is more enough to break a bond between carbon and chlorine. This is how the energy is generated within the molecule, and that is utilized to undergo the reaction. And this breaking of the bond between carbon and halogen, where the carbon takes the bond electron and goes away from the carbon, thus it forms chloride ion and a methanol is formed. And in the transition state, yes, if you just look at, it looks like a wheel shape where the carbon is forming 5 bonds, pentavalent, but actually the carbon is tetravalent. So it always wants to become a tetravalent. So it here in the transition state, it eliminates chloride ion, and thus what is formed is tetravalent carbon is formed and methanol is formed. This is what the reaction mechanism involved in this particular reaction. Now coming to the stereochemistry of this. Stereochemistry, wherein in this stereochemistry, we cannot use the same molecule that methyl chloride, because methyl chloride is just simple example to understand the mechanism. But here, this carbon is not a chiral carbon. So, or in other words, it's not an optically active compound. So we cannot use the same molecule to understand the mechanism, understand the stereochemistry. So what I am using is the another molecule which is optically active, that is 2-bromo-octane, and which is a Leo rotatory, that is minus sign. This Leo rotatory form of 2-bromo-octane, where the bromine is on the right side, and this is attached with the chiral carbon. Chiral carbon means carbon attached with 4 different atoms is called chiral carbon, which is optically active carbon. So this optically active molecule, optically active means the compound which can rotate plane polarized right towards either right side or left side is known as the optical activity. And this optical active molecule is a Leo form of this particular molecule, where it is Leo 2-bromo-octane is going to react with a nucleophile. And this nucleophile is going to attack at the rear side, because at the front side there is a bromine. So it attacks at the rear side to form two octanol, but here the minus sign is converted to plus sign. That is after 2-octanol, what it is formed, it is a dextrorotatory. That means it rotates the plane polarized right towards right side. So it is dextrorotatory. Whereas your reactant is Leo rotatory, it rotates towards left side. So it's a Leo rotatory. So the change in the configuration takes place by the attack of this nucleophile. So because it attacks at the rear side, it forms dextrorotatory form of this. The configuration is changed. Whereas the H what you're finding here in this case is on the left side, and in this case it is on, in the product it is on the right side. So because of this, what we call it as the inversion of configuration takes place. Inversion of configuration takes place. Where it's called as Walden inversion. What is that inversion of configuration? The Leo form is converted to dextro form, or dextro form is converted to Leo form, or in other words, the hydrogen in the reactant, it is on left side, and the hydrogen in the product, it is on the right side. So which leads to inversion of configuration takes place, or it is also called as Walden inversion. This Walden inversion is, the Walden is the name of the scientist who discovered this, and it is named after him as Walden inversion. So the stereochemistry involved in this SN2 reaction is there is an inversion of configuration takes place. Clear? And the next point in this SN2 reaction is reactivity. So in this reactivity, always the methyl halide reacts faster than primary alkyl halide. Primary will react faster than secondary. Secondary will react faster than tertiary. This is what the reactivity with respect to alkyl halides, different alkyl halides. So methyl halide reacts faster than primary. Primary will react faster than secondary. Secondary will react faster than tertiary. This is what the reactivity involved in this particular SN2 reaction. Clear? So I'll just summarize this once again. Nucleophilic substitution bimolecular reaction, which is denoted by SN2 reaction, SN2, SN2, S capital, N capital, and 2, which is nucleophilic substitution bimolecular reaction. Coming to the definition, the methyl chloride is going to react with a nucleophile to form methanol and a chloride ion. This reaction is known as SN2 reaction, or a nucleophilic substitution bimolecular reaction. Clear? Coming to kinetics of this, in kinetics, it follows second order kinetics, which indicates that is the rate of reaction depends upon the concentration of both the reactants, that is alkyl halide as well as nucleophile. Alkyl halide as well as nucleophile. Since the concentration of both the reactants are very important, that's why this reaction is termed as second order kinetics. It's a second order kinetics. Coming to mechanism, in mechanism, the nucleophile is going to attack alkyl halide, that is methyl chloride, and this nucleophile, the OH, cannot act on front side because on front side is the chlorine atom, and that chlorine will always electronegative in nature. There is a repulsion between both of them. That is, nucleophile is also rich in electron, chlorine is also rich in electron, so that OH or the nucleophile cannot attack on front side. It will always attack on the rear side, which is also called, it is always attacking at the back side. So when it attaches at the back side and in a transition state, it looks like there's a bond formation between O and carbon, and there is a bond breaking between carbon and chlorine halogen. Thus, the transition state, the carbon is pentavalent. It wants to become a tetravalent, so it eliminates chlorine as chloride ion, and ultimately what is formed is a methanol is formed. This reaction, this mechanism is a single step mechanism where it follows second order kinetics. That means the rate of reaction depends upon the concentration of both the reactants. Then coming to stereochemistry. So in stereochemistry, we cannot use the same methyl chloride because it is not optically active molecule, where it does not contain any chiral center. Chiral carbon means it's carbon attached with 4 different atoms or groups is called chiral carbon, and that particular chiral carbon is optically active. Optical activity means it can rotate plane polarized light towards either left side or right side. This is called optically active, what we call. And here I am using the example as 2-bromo-octane, which is a Leo rotatory, which indicates minus sign. It's a Leo rotatory. This Leo rotatory 2-bromo-octane reacts with a nucleophile OH to form 2-octanol. And here what we are saying is a positive, the sign is there, that is plus 2-octanol is formed. That means we are it has converted from Leo form to dextro form. From Leo form to dextro form. And when we look at this particular stereochemistry, the hydrogen is present on left side where the bromine is attached to that particular carbon. If you just look at this particular carbon, which is a chiral carbon, So hydrogen is on left side, bromine is on right side. Whereas in case of the product 2-octanol, the hydrogen is on right side and the OH attacks at the left side. So what we call it as is in the case of the stereochemistry, there is an inversion of configuration takes place. There is a inversion of configuration takes place. That means the Leo form is converted to dextro. Sorry, the Leo form is converted to dextro form, or dextro form is converted to Leo form. This process leads to inversion of configuration takes place, or is also called as Walden inversion, because Walden is the name of a scientist who discovered this particular stereochemistry of SN2. So it is called as Walden inversion, or it is actually in chemistry, it is inversion of configuration takes place. The configuration is reversed. So where the hydrogen is attached on left side, it is converted to right side, or the Leo form is converted to dextro form. Leo form of a reactant is converted to dextro form of a product. This is what stereochemistry involved in this SN2 reaction. Coming to the reactivity, in this reactivity, the methyl halide is going to react faster than primary alkyl halide, and primary alkyl halide is going to react faster than secondary. Secondary is going to react faster than tertiary. This is what the reactivity involved in this particular SN2 reaction. Clear? Thank you.